Okay, so welcome back for this afternoon. I know in Reading we had a very nice lunch, and we're now moving to the afternoon session. So our first speaker this afternoon is Dr. Ashish Darbari. Before I introduce Ashish, I just want to say a couple of thank yous to Ashish, because Ashish does help us put this event on and help us get the speakers. So firstly, a big thank you to Ashish for that, and also for those not in Reading, they can't see Ashish sat in a chair. Ashish had quite a bad accident a while ago, but he struggled here today to give his talk, so thank you to him for that as well. Ashish is the principal hardware design engineer at Imagination. The title of his talk is Using Abstractions for Effective Formal Lessons from the Trenches. Dr. Ashish Darbari works at Imaginations Technologies. He has been working for 15 years in the field of formal, where he has published 20+ papers and holds 5 patents. He has a doctorate in computer science from Oxford and is a fellow of the British Computing Society and IETE. Also a senior member of the IEEE and ACM. Since March 2015, he is a Royal Academy of Engineering visiting professor at the Electronics and Computer Science Department at the University of Southampton. And we're going to hand over to Ashish now. Thank you.
Can everybody hear me?
Yes.
Okay, great. So apologies for having to sit and give this talk. I didn't imagine I'll be doing that one day. But I thought it would be nice to take a break from home, where I've been resting for the past couple of months, and meet some of the fellow community people interested in the formal verification. This is joint work with my colleagues in AVM group, Advanced Verification Methodology group, Ian Singleton, Neil Dunlop, and Alex Netterville. Alex is here. Ian and Neil couldn't join us today. This is part of some of the work that we've been trying to do at Imagination for some time, and this is a talk that I've given previously in Jasper user group last year, and I thought it might be useful to share this with the UK side. So let me start off by asking, what are we worried about these days? And the answer that everybody knows is everybody's talking about shift left, start verification early. A lot of the people talk about designer bring up, and things like linting, using interface properties, standard bus protocols, get your X's out, run CDC checks if you have multiple clocks, connectivity checking and the like if you're into SOC. Register access stuff, all of the standard stuff that EDA vendors tell you can do this automatically out of the box. The problem that verification is all about is, on top of all of the designer bring up phase, is do bug hunting, find proofs. So as I talk about bug hunting flows, building proofs, then the debug and the coverage and the review and the reuse, all of these are issues connected to verification. So what are we actually going to do about, so I talked about these automated apps and VIP components and so on. For verification, as in if you're trying to actually get deeper in the bug space and want to actually do full-on formal verification, trying to prove absence of bugs whenever you can, then you need a little bit more than just the tool and its related apps. At least that's my humble view. You need a good strategy. You need awesome solvers engines, which most of the standard formal verification tool vendors will give you. And you need some nice flows. Methodology is the key. And one thing that I wanted to share with you today in the talk is abstraction and what abstraction can do for you in actually driving a better methodology. As systems become more and more complex, we've got to revisit something that has been as old as 40 years. So I don't know how many of you here are formal verification background in academia, but Patrick Cuso and Radia Cuso in 1977 wrote a wonderful paper on abstract interpretation, deeply mathematical, but that laid the ground for a lot of abstraction work to come in the remaining years. This is not an exhaustive list. If you Google for abstraction or if you Google for things like that, you'll get tons and tons of papers. And I did spend some time making this slide thinking whether I'm doing justice to some of my forefathers in the field. And And I've come to the conclusion that actually a lot of the work that was done in 77 has been very useful, but actually very restricted in its application. Tom Mellem did a wonderful PhD in Cambridge and talked about using abstractions for hardware. And then I think the definitive milestones came during the time action work has been done, so that these guys wrote. And as you can see, there has been a big gap from 77 to 90. But then from 90 onwards, there has been a constant strife to get better and better at abstraction, and different people trying to study it. This is, by the way, only for hardware abstraction, so there's a lot of work done for software side as well, which I haven't talked about here. So then, in 2003, basically, there was counterexample guided abstraction refinement, which was a big deal. It made a big difference in computing automatic abstractions. I have a problem, actually, having said that all of these people did fundamental, useful work. I think every time I go back and look at these papers, my feeling is that an average engineer who's working in design verification in industry will not understand most of these papers. They are amazing in technical content, written with precise things in mind, but they're not very easy to understand, and you need a solid formal education in the background to be able to absorb this. However, in 2011, the OSCE guys did some work, I think, with the Cadence guys, and they published this nice paper, which is on end-to-end formal using abstractions. And this is a really nice paper in the sense that actually it speaks a language that most of the design engineers who write Verilog and VHDL do understand. So all of this has been happening, right? So what did we do meanwhile? So I'll talk about it, but let me just say the difference between proofs versus bug hunting. So we heard the talk from Cadence on bug hunting and how bug hunting is a very useful tactic, because as engineers, as verification people, we need to find every little bug and deepest of bugs. Proofs are also very useful to build, especially for safety critical systems. An abstraction is a double-edged sword. So when you're actually trying to do some abstraction, you could actually overdo it, and you might actually end up getting more failures, or you could actually underdo it. So if you overdo it, as in if you over-constrain, and if you over-abstract, you will get false positives, passes, and if you are underdoing it, then you'll start getting failures. So it's not something which is completely automatic, and that's why the adoption has been not great. Traditionally, it has been considered a black art. And most of the time, you need domain experts best suited to address these issues. The biggest challenge is in how much general I should go and how much specific I should be. But then we would like to consider other aspects of deploying abstractions. For example, can we reuse them? Can we review these? Can we sign off our verification with these? And are we talking about architectural abstractions or micro-architecturals? I think John this morning spoke about high-level systems modeling and abstractions at an architectural level. So this is more at a micro-architecture level. So we started to publish some of the initial results in 2014. We published a DAC paper on single transaction abstraction, where we showed how to verify ordering and data integrity properties. And the same year, we went to a Cadence event in Munich and presented some comparison on abstraction models. Then we started to explore a lot more about what we can do internally going from these things. And in DAC 2015, we actually did some work, presented the work on verification of arbiters. So they're all connected. None of this is in silo. And this year, we got a UK patent issued to us for the arbiter verification work. So let me actually present to you some case studies and actually show you what we are talking about and how they are connected to each other. So a lot of the people will tell you, Ashish is hung up on a FIFO. Yeah, I am hung up on a FIFO because guess what? Most of the bugs are related to FIFO. Like it or not, they are around counters, they are around FSMs, they're around these numpty things that we overlook quite easily. The other part is why we are interested in solving this problem is because ordering is an essential aspect to design these days, because designers use it aggressively for optimization, and FIFOs are used everywhere. Any high-performance system you can look at, whether you're talking about GPU, CPU, networking, SoC, you cannot not see these things. So we talked about two-transaction abstraction. What we were talking about is this. So imagine a block diagram with the right handshake on a write request and a write ACK, sending write data into the design, and being read out on a read handshake, and you read the data R data. So in formal, we don't do what we do in simulation, as most of you will know. We tend to go symbolic, and we actually start monitoring symbolic values. So this piece of work was actually done because I was working with the Cadence AE, Vince Reynolds, who's sitting here, and Vince was telling me that Cadence had their own scoreboard. And in fact, I don't know if Vince you said, but there were suggestions being made to me that I was unnecessarily wasting my time, and I could just go and reuse what an EDA vendor has. And I thought I was wasting my time, but sometimes it's good to waste your time. So I decided to waste a little bit more time on this, and we came up with this methodology where we said we could actually build a verification environment where we will verify any arbitrary FIFO. However it is implemented, we don't care. And the test bench that we are going to use is actually shown on this PowerPoint slide. So it actually starts off by assuming that you have two non-deterministic values, D1 and D2, in your system. And we could send these in a predetermined order into the design. And we will then make the claim that they will always come out in the correct order, as in whatever had gone in first would come out first. So the basic modeling logic around this is actually quite simple. A lot of the people think it's naive. But now this is the other end of the spectrum, 1977 down to this. This is now so simple that once people do understand how it is working, they find it hard to believe that it works. Because how could it work? It is so simple. But the reason it works is because it's actually doing something very simple. It's actually tracking two arbitrary values. And what model checkers do under the hood is they would instantiate these two symbolic values with all possible instances of specific values. And they will try and create all of the interleavings of D1 and D2. So what I'm saying here is you have registers, which I call these sampling registers on the input interface, sampled in D1 and sampled in D2, and on the output interface, sampled out D1 and sampled out D2. And they get set when we actually, when certain conditions are met. So for example, sampled in D1 would be set when the watch data value appears on the input interface, and we have not sampled in D1 already, and we had a right handshake to read this value. And once this gets set, it remains set. It's a sticky flop. Sample out D1 gets set when you have sampled in this watched value, and you had a read request. So in this particular FIFO, there is a 1 cycle latency between when the read is issued and when the data comes out. So we are trying to make sure that we catch that possibility. So we invent another flop, which is seen read request. And that basically captures the fact that you had a pop in the current cycle or you had one before. So once you've had it, and this is also to avoid the errors 1 cycle after reset. So you had a sample on D1, you've got this handshake going, and the watched value appears on the output, you just set this register. And for D2, you do the same. It's actually symmetric. So all we do is set up these modeling code. It's almost like if you were doing simulations, set up a scoreboard, except in this case, it's a symbolic scoreboard. What you do then is you stake a claim, which says sampled in D1 and sampled in D2. Then it's either the case that D1 has come out or D2 hasn't come out. Or essentially, we are saying we could have written this as an implication to say if D1, then D2, meaning the D1 register must get sampled out D1 must get set before sampled out D2. What I'm not showing you here are the site constraints, which are that D1 must go before D2. So actually, this model is quite simple, and we use this internally to verify our internal FIFOs. We then presented in DAC what we call as a smart tracker abstraction. Called it smart tracker because one of the days I just wanted to create a local copy of this, and I didn't have a better name for it. It's now referred to as a smart tracker, so call it smart tracker now. It is a smart, and it is smarter than actually the two transactions abstraction, because in this case, we're only tracking one transaction. And by only tracking one symbolic transaction, we can prove exhaustively that an ordered device works correctly. And how does that supposed to work? Because this is counterintuitive, because if you ask anybody from a high-level modeling point of view, people will say you at least need two values to be able to make a claim about ordering. So this is now taking the game of abstraction to a slightly different level, and we're saying, look, what we will do is we'll have a tracking counter here, which will increment on every value that appears in. So anytime you have a value that goes in your underlying DUT, we'll just increment this counter. Every time you read out the value of the DUT, you decrement the counter. But you freeze the count as soon as you see the washed value go inside the design. And that count at that time will give you how many elements are ahead of this washed value. So now you know that when the counter reaches 1, you expect to see the washed value appear on the output interface. So this abstraction essentially is built very similar to the previous one, except that we're only tracking one value and we're using a tracking counter here. What happens then is the property then becomes when you can read, meaning the count has become 1, you had sampled in, seen the washed value, you had a push as in a right handshake, etc. Then a cycle later, because this design has a cycle latency in read, the washed value appears out. Okay, so these abstractions are useful, but they're not enough. So what we do is we now provide this extra layer. And this is where we were able to do something that the cadence scoreboards did not do by default. And this is something that became apparent on a closer examination. And that's how we went about publishing the results. What we did was we had a counter. So I think the problem I had always with formal verification perception in everywhere is people go by these hypes. So for example, if you open some formal tools, you will see counter abstraction, this abstraction. A lot of the people believe a counter is a bad thing. FIFO is a bad thing. Just black box it, get rid of it. You know, you've got to be a little bit more careful about what we are trying to achieve. Here a counter was a good thing. Interestingly, the cadence scoreboard looked very similar to how my two-transaction model looked, except that it was so simple that you couldn't add any invariants in it. So what I did here was I exploited the fact that I had a counter. I exploited the fact that I was actually having a slightly richer thing to play with, and I started adding auxiliary helper properties, which I call invariants. Invariants technically in the literature are called properties that are always true of your design from reset. And when you're talking about putting another formal test bench, then you're talking about invariants that are true of both the test bench and the design. So actually, they're conceptually very simple. They're just assert properties. But the good thing is, you are now reducing exponential state space search into linear, or as you would see sometimes, near constant amount. So what happens is once you prove these properties and you then assume them and you tell the tool that actually, look, these are good properties, you know, the system just proved it, I'm telling you. The tool then uses this information to prove the state space search massively. And the results you will see in a little bit. But what are these invariants, for example, for the FIFO DUT? Principally, what we are saying is, look, we are just incrementing and decrementing this tracking counter as and when we like. And we don't know when the tool will decide to send this washed value in. Unlike simulation, where we create the stimulus sequence and we decide what to send, I don't choose anything. I'm only sitting here observing. My model is sitting as an observer logic. It is not creating any input sequence to send D1 at any particular point of time. Sorry, a washed value D in a single transaction case, for example. So because there is this non-determinism in terms of timing as to when this value gets sampled, we don't actually know where in the FIFO this would be sitting at any given point of time. So what we do is try and prove this hardest invariant, which is we call the positional invariant, which tells the tool where exactly in the DUT the tracked value is sitting. And we work it out because we know a little bit more about the microarchitecture of the design, so we are able to make relationships between read pointers, write pointers, and the tracking counter. However, as I said, it's hard to prove this invariant, and it takes a lot of effort to get this right. So how about making it one step simpler? Guess what? This is assume guarantee. Not exactly the assume guarantee that Ken Macmillan and the others proposed 15, 16 years ago, but something similar. Here now we say once the tracked value is in the system, then the tracking counter is in between the read and the write pointers. There's got to be. If the tracking value has not entered the system, then the counts between the DUT and the abstract model agree. Meaning, not tracking value has not entered, then tracking counter and the DUT will agree in their counts. Now these invariants are slightly simpler to prove than the purple one. But they can also be quite hard as the depth of the FIFO keeps on increasing. So we come up even with a one more simple invariant, which is if the tracking value has not entered in the system, then it couldn't have left it. Quite obvious, common sense. People think, why would you need that? You need that because once you get that, the blue ones go through. And once the tracking value has entered and exited that system, then the counters agree. So the black ones are actually the simplest ones, even for 8000 FIFO, they prove within seconds. And now what we will do is, once you've actually proven these, you assume from black to blue to purple, and you start getting these proofs quicker and quicker. Still hasn't proven the ordering property yet. We're still trying to prove the positional invariant. But once the positional invariant is proven, we can assume that. And that actually has an amazing effect on the time scales of the ordering property. And the amazing effect is shown here. On the left-hand side is the curve for 2 transactions, and on the right-hand side it is for the single transaction, or smart tracker as we call it. Now the red lines are actually proof times, CPU proof times, to prove the positional invariant with the assumed guarantee flow and the auxiliary invariants that I showed to you on the previous slide. And the blue line is the time that it takes to prove the ordering property once the positional invariant is proven and assumed. Now you would notice, because the 2 transaction abstraction is tracking more, a little bit more than the single one, the slopes are a lot more steeper. So the red one specifically, the slope is steeper than the red line on the right-hand side. However, look at the nice linearity, right, on a design that is increasing in exponential format. And if you look at the blue line, I mean, for an 8192 D FIFO using a smart tracker, we are talking about spending 500 seconds to prove exhaustively that the FIFO is correct. 500 seconds. So that's that. Now what happens here is, if you take a closer look at the single transaction one, if you don't use any of the flows, you don't use invariants, you run out of steam at about 32 deep. So you're unable to prove the invariant after about 24 hours, and you're unable to prove anything else. So this is, by the way, this much amount of state, okay? 500x scalability refers to the comparisons we made to the cadence scoreboard. Now, I've got 10 minutes left, I'm told, so I've been going quite slow. So I've got an arbiter now. I want to just show you what an arbiter can, how an arbiter can be verified. So I just wanted to show you one slide quickly to show the correspondence of an arbiter to a FIFO. This particular arbiter actually has 4 inputs on the input interface. More than one requester, more than one input can go high, and they can arbitrate. And the arbiter has to arbitrate over requests, and it will send the output to one of the 4 output interfaces. The thing that we noticed is actually the correspondence between FIFO and arbiter is astonishing. In fact, all we need now is another watched value concept, except that we were watching a requester here rather than a value. And then what we do is, it's a standard business of getting the handshake signals right, which is an OR of the input and the output handshake signals. And then you increment on a global input handshake if you haven't sampled, and again, the decrement on an output handshake. You have a tracking counter. You have a sampled in, you have a sampled out. And actually, the can read is again shown in the smart tracker is here when the count goes 1 sampled in, and you have an output global handshake. Interestingly, the property here is exactly the same as we use for the FIFO. Believe me or not, but this one model shown on this slide can verify a range of different arbiters. The only changes we need to make are changes that correspond to the slight way the arbitration policy works. That is, adjusting your tracking counter and adjusting your increment and the decrement terms. So we tested this, and we saw that they were actually, this was scaling rather well, and we didn't even put any invariants in this. This was just vanilla abstraction. So we got some good results on this one, up to 256 requesters, and round robin and so on. Did a lot of additional work to make sure we did not fool ourselves. Code coverage, assertion properties with traces that come in some of the tools. We also did hand mutation on the actual design to see whether by breaking the design we can actually find a bug. So it all looked good. However, when the design becomes more and more complex and systems become subsystems, as in blocks become subsystems, things get more interesting. So this memory subsystem one is an example of an arbiter that sits in one of our memory subsystems which arbitrates over 9 requesters, and it can actually send the data to any of the 8 memory banks. This one isn't very flop heavy, so I don't want to tell you that it had 1 million flops. It didn't. It actually had, a few thousand flops, but it had enough control in it to cause us headache if we did vanilla formal verification. It's an animation to say concurrently all of this could be in flight, multiple transactions originating. Now what is happening in this design is that R0 and up to R3 are in one group, and R4 to R7 is another group. And essentially, if requests from different groups were actually, if requesters from different group were competing for the same bank, anything is allowed. Any request can arrive, and there is no rule here. What depends on the latency of the previous transactions. However, if you have a stream of requests originating from one requester Ri being sent to a requester Bj, then first come, first serve is the rule. However, if you have requesters in the same group getting active in the same clock cycle, sending to the same bank, then the rule is priority, and the requesters with the lower index will take priority over higher index requesters. So we've got a couple of things going on here, interesting challenges. What we did actually in this case was a combination of the smart tracker and extensions of two-transaction abstraction. So what we did is for the first come, first serve, it really is a smart tracker, which we just bolt on through normal automation. For the priority, it was almost like the arbiter case. We did do a little bit better than that this time, because the problem with that arbiter solution was that this wasn't scaling as the number of requesters were increasing in this design. So we went down the route of doing extensive case splits. And we took the case that what if 2 were active at a time, 3 were active at a time, and 4 were active at a time. We did all of this in an automated way, one-off, so it could be reused. So we did all of that partitioning, and you can see it increased the number of assertions we got for the priority. For first come, first serve, it's quite straightforward. It's 8 times 9, 72 asserts. But we had 11 different cases per bank, times 2 times 8 banks. So it's 176 asserts are spit out here, but all prove relatively quickly. Overall, it's about less than 1,000 lines of code. A lot of this is because of repeated assignments to wires, etc., which we can trim down on. How much time have I got, Sarah? 5 more minutes. Okay, so I want to discuss quickly an unpacker. Now, this is completely different from a FIFO, completely different from a memory subsystem. It's a video unpacker. As one of my colleagues, Neil, did work on this. And for illustration's sake, we have a YUV traffic going in, and we have valid enable protocol driving data in. And essentially, the requirements here, the ones that actually will cause you a lot of problems in verification is data integrity checks. Am I duplicating the data, loss, modification, swapping, extra spurious data? One-to-one correspondence between what is received and what is sent is required. And essentially, it's, as I said, it's data transmission, but there are different pixel formats. And as it is a video pipeline, you don't have a straightforward tracking counter here. It will just count on a single push. So we've got to be a little bit clever about this. And Neil is very clever. So he came up with a very interesting tracking counter principle, which is how do we increment? The watch data could be sitting in any one of these packets. So it could be sampled at 0 or it could be sampled at 7. So you just create these declarations. And increment can actually happen on the very first one, because you could have seen the watched value there, or the watched value could be in any one of the subsequent streams. As long as we are tracking that watched value safely through, we are done. And the tool will try and put that watched value in any of these streams. So if you look at the structure of this, it looks very similar, except that increment is now adjusted accordingly. And the property becomes a vertical blanking is on, and the format of the pixel is some known thing that we want to check. Then once we are ready to sample out, data out is the wash data value. It literally is an incarnation of Smart Tracker. So we got interesting things. I'll skip these 2 slides and move on to another interesting case study. We found loads of bugs with that and did exhaustive proofs. Alex, who's sitting here, worked on this. Is a scheduler that sits in one of our subsystems. And as with every instruction scheduler, there are hazards and dependencies. And there is this ordering and out of ordering. And as I said, you look around and it's present everywhere. So what we did here was create a window of washed transactions, instructions, T0 to T7, and basically we create these sampling windows. And essentially, the tool will pick any one of these to track, and the claims that you're going to make for assertions will check any one of these non-deterministically. The thing here that is tricky is that the next state is again determined based on a lot of sequential history and complex FSM tracking. So, the challenges are, of course, more, and then there are a lot like n+1 transactions shown here, but we have tried to take 8 at a time window, so that there's more to control and there's more to. It's not completely automatic. But what we can say, or what we do need to check, for example, is that if you have an in-flight wash transaction to a valid cache line, and the transaction is a write, and followed from that, if there's an instruction, it's a following subsequent wash transaction which is also valid, and it's a read, and so write has happened before the read. So what we need to say is if they're both to the same cache line, then the write is seen before the read. And if you look at the correspondence of this property with what I talked about with the 542 transaction, it's the same skeleton. And a lot of the modeling code is pretty similar. So we got some interesting results. We had explored, which is a terminology in some of the cadence tools to mean their proofs were inconclusive. We did have some inconclusive proofs. We had some failures, which we're looking at, and quite a few passes. We didn't find RTL bugs yet, but in this case and in the memory subsystem case, we were verifying the design, when it was already verified with simulation. So this was almost a year after it was verified with simulation. So we weren't doing this in a rush, as it were. So in summary, what we're saying here is that abstraction is a useful technology. I hope that this presentation would help you look at this and say, it's certainly doable and it's not as hard as some of the maths that has been published in the last 40 years. It's a very powerful technology, and if you are into designing automated test bench solutions, then that's the way to go. We claim that actually with abstraction and formal, you can have a better shift-left verification strategy. And in that sense, I believe it's a very powerful app in the way that EDA vendors package app. But it's an app on a more fundamental level. Questions?
There is one online, and I'm not sure if you're allowed to answer this or not, but I'll ask it. Which simulation and verification tools are being used at Imagination?
That question, I'm not sure if I know the answer to. We use the tools that the EDA vendors make.
Okay.
One or more of these.
That's a good answer, I think.
Yogesh from Ericsson. You mentioned using hand mutation. Have you had an experience with Certitude and proving the models?
Yes. So Anthony is sitting here, is a big fan of Certitude, and we have animated discussions about using Certitude. So I would use Certitude once I have actually done enough hand mutation. The only complaint I have against Certitude is I don't have the ability to control how many interesting mutations it will actually insert and who will sit through and wave all of these. Whereas if I'm designing a subsystem where I know fairly well what the requirements are, and most of the bugs, interesting bugs actually, are around control, I could very easily go and screw up the control by hand, quite randomly so, right? Spend a day, let's say, picking 30, 40 different control-based bugs, but I'll be able to get the failures if the tests are, if the asserts are good. That, in my view, is a much better use of my time. Now, once I've done that and I've got enough confidence and I've got enough hours in the day, farm out Certitudes, farm out tens of different tools that are Certitude-like, and get the regression failures. Do this. I think the problem I have is I don't know the bound and the time, and I think Anthony and I often have these discussions, and we don't often agree on this, but I think it has its place once you've actually done enough sensible thing. I quite like reviews because I think reviews tend to catch a lot of interesting issues as well. I think certitude will have a place in ISO 26262 type for it, but again, unless they make the tool better, sorry, without any offense to Synopsys guys, unless you make it more tighter and more intelligent, the mutations are very, very, I mean, the kind of bugs we are planting, right? It's like if this value came in and in the flight that value got changed and the bug basically was in a transaction after this and it changed it. No tool can do all of that, right? We've actually found issues in our test benches, pathological cases through that kind of thing. It's just because we are thinking bug, 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 right? So.
Okay, any more questions? I just have one question. So, have you ever contemplated the completeness of some of the properties you're trying to prove?
Yeah, so
I'd be convinced that the FIFO property was complete.
Yeah.
For more complex.
So as I said, when we are looking at these things, we are going from a high-level requirements point of view, and actually looking at. So ordering is not the only checks that we did for all the other designs, but there were certainly some of the most challenging ones. We obviously look at what needs to be verified for a design, look at the requirements, and then make those judgments. I don't believe a machine-based tool can do this today. That's my opinion. Once we have actually got the model, and the model is tricky because it is tracking a lot of different things, especially on a bigger design, hand-based mutation and a review helps a long way. I don't know if you have any other magic bullet that helps you, but for me,
only by sort of metaproofs. It's a bigger topic.
Yeah.
Okay. Okay. Thank you very much. Thank you.